So in the last lecture, we left off talking about caches. So we're going to continue on that theme today. And to begin with, what I'd like to do is discuss some of the reasons that cache misses can occur. Essentially, we can categorize the different reasons for cache misses, and this is what I'd like to look at here. So the first type of cache miss that we can have is what's referred to as a compulsory miss, or sometimes a cold miss. And this is a miss that's due to the address that's being accessed for the very first time. And compulsory misses are impossible to avoid. You're obviously going to need to bring the data into the cache the very first time it's ever accessed. This is unavoidable. Even if you have an infinite size cache, this would not help you to avoid compulsory misses. The next type of miss is what's called a capacity miss. And this is a type of miss that's due to the cache not being large enough. Effectively, the program is trying to use more memory than what can be fit into the cache. And because of this, from time to time, blocks are going to get evicted. And then when the program later accesses the data associated with those blocks that were evicted, it will get a miss, a capacity miss. The next type of miss is what's called a conflict miss. And this is a miss that's due to limited associativity of the cache. And essentially, it's a miss that would have been avoided if you were using a fully associative cache. And this essentially happens when too many blocks in memory are mapped to the same set in the cache. And essentially what you can get is sort of a thrashing effect where many, many different blocks that are being accessed by the program in memory are all getting mapped into the same set. And then you don't have enough space within that set to hold all the entries all the blocks from memory that you'd like to hold. But maybe the other sets are not really being used very much in the cache. The next type of miss I'd like to talk about is what's called a coherence miss. I'm not going to really go into this in much detail here. It's something that relates to concurrency. Concurrent programming. If you have a multi-processor environment, the processors will sometimes have to flush each other's caches in order to keep their picture of memory consistent. So we may come back to this later when we look at concurrency. And true sharing and false sharing misses basically pertain to coherence misses. There are essentially different reasons for coherence misses occurring. Next thing I'd like to talk about is virtual memory. And virtual memory is essentially a memory management technique that allows processes to be able to access more memory than there is physical memory on the system. In addition to this, it also allows processes to share memory and also to provide memory protection so that for example, one process can't access the memory of another process, or a process is restricted in whether it can read and write to some of its own memory. And in this particular approach, each process has its own virtual address space. And whenever a memory access is made, these are always using virtual addresses. And then there's something called a memory management unit, or MMU, which translates these virtual addresses into physical addresses. And the physical addresses are what the hardware really understands. When you go to access data in RAM, for example, in the computer in memory, you give it a physical address. This is the only thing the hardware understands. So there has to be some kind of translation between virtual addresses and physical addresses. And this is done by the MMU. With virtual memory, things work in the following way. So we have our physical address space, which corresponds to the RAM on our system, the physical memory. And we take and partition it into consecutive regions of p bytes each, where p is referred to as the page size. So for example, the first p bytes in memory would correspond to physical page number 0. And then the second p bytes in memory would correspond to physical page number 1, and so on all the way down to m-1, where m is the number of physical pages in memory. And we do a similar thing with the virtual address space. It's also partitioned into pages of size p. So the first p bytes in the virtual address space would correspond to virtual page number 0, and then the second p bytes would correspond to virtual page number 1, and so on all the way down to n-1, where n is the number of virtual pages in the system. And typically n is much larger than m. So in other words, the virtual address space is typically larger than the physical address space. Because a program is typically running in a virtual address space, and the hardware really only understands the notion of physical addresses when you're trying to access the RAM chips, for example, there needs to be a translation from virtual addresses into physical addresses. And the way that this works is on the basis of pages. So we map virtual pages into physical pages. So for each page in the virtual address space, we can map it to a particular page in the physical address space. So for example, in this diagram here, virtual page number 0, which is marked by red here, is mapped into physical page 0 in the physical address space. And then virtual page number 1 is mapped into physical page number 6. and virtual page number 2 is mapped into physical page number 4, and virtual page number 6 is mapped into physical page number 1. And we can also have things like what's marked by these X's here, where effectively there's no mapping at all. So if we try to access one of these virtual pages that's marked by an X, there is no mapping. Therefore, there's not actually any underlying memory associated with this portion of the virtual address space. And typically you'll get some kind of hardware exception from the processor saying you're making invalid memory access, because essentially there is no memory associated with this region of the virtual address space. On this slide, I'd like to elaborate more on how address translation takes place. In other words, how we map from virtual addresses to physical addresses. So every virtual address is partitioned into 2 parts. There's a page offset, which corresponds to the lesser significant bits, and a virtual page number, which corresponds to the more significant bits. And the number of bits that's allocated to the page offset is simply log base 2 of p, where p is the page size of the system. In a similar way, we also partition the physical addresses into a page offset part and a physical page number. And again, because the size of a physical page and a virtual page is the same, in other words, they're always p bytes, the number of bits that's needed for the page offset in the case of a physical address is the same as in the case of a virtual address. It's log base 2 of p. And then the remaining bits, the more significant bits, correspond to a physical page number. And because the number of bits in the virtual address and physical address don't have to be the same, and generally the number of bits in the virtual address tends to be more than the number of bits in a physical address, for this reason, the size of the virtual page number in bits is typically larger than the size of the physical page number in bits. And one important thing to understand about address translation is when we're mapping from virtual addresses to physical addresses, essentially all we're doing is we're changing the bits that correspond to a page number to a potentially different page number, but the page offsets never change. So the only thing that's affected by address translation is the page number part of the address. At this point, I'd like to do a few exercises. So let's consider a system with the following virtual and physical memory parameters. Virtual addresses are 16 bits. Physical addresses are 12 bits, and the page size is 256 bytes. So if, for example, we wanted to find the number of virtual pages, we just take the total number of virtual addresses, which in this case would be 2 to the 16, since we have 16-bit virtual addresses, and divide by the page size, which is 2 to the 8, which gives us 256. If we want to find the number of physical pages, we would divide the total number of physical addresses, which was 2 to the 12, since there's 12-bit physical addresses, and divide by the page size, which gives us 16. If we want to find the number of bits in the page offset, this is simply going to be log base 2 of the page size, which is 256, which gives us 8. If we want to know the number of bits in the virtual page number, what we do is we take the total number of bits in the virtual address, which is 16, and we subtract the ones that are used for the page offset, which is 8, which leaves us with 8 bits. And if we want to find the number of bits in the physical page number, we take the total number of bits in a physical address, which is 12, and we subtract the number of bits which are used for the page offset, which is 8, which gives us 4. So on this slide, I'd like to consider a simple address translation example. So for the purposes of this example, we're going to use the same system as in the example on the previous slide. In other words, we have a system where the virtual addresses are 16 bits, the physical addresses are 12 bits, and the page size is 256 bytes. And we can imagine that the particular data structures used by the processor are basically storing the following information in terms of mapping between virtual pages and physical pages. This abstracts away the true reality of how systems do things, typically using data structures called page tables and so on. But this is sufficient for our needs here. So effectively, somehow the processor maintains this kind of state information. So for each virtual page, there's a corresponding physical page number that's maintained in some flag saying whether you're allowed to read and write the memory or whether you can execute instructions that is in the memory for that particular page. And now suppose that we want to consider various different translations that might take place. So for example, suppose that we're trying to do a read from memory for the purposes of reading data from the virtual address, which is given by this address here in binary, which I think is 8 ones followed by 8 zeros or something like that approximately. So the first thing the processor has to do is it has to partition the virtual address into the page number part of the address and the page offset part of the address. So in this particular system, the page offset is 8 bits. So the least significant 8 bits, which are all zeros here, become the page offset. And the remaining bits, the more significant ones, are the page number, the virtual page number. So essentially what would happen is the processor would then go to this information that's given up above here, looking to see, is there an entry in the table for this particular virtual page number? So as you're looking through here, you notice that there is no virtual page number for 11111111. Therefore, this is not a valid mapping. So the processor would generate some kind of access violation, essentially saying that there is no such virtual address in the address space that you're trying to do this memory access in. Suppose now that we tried to do an instruction fetch from address 0 in the virtual address space. Again, the address would get partitioned into a page number. The more significant bits, which are all zeros, would become the page number, and the 8 least significant bits would become the page offset. So we're going to be looking for an entry with virtual page number 0 in the above table. So we go scanning through the table here, and there is actually an entry for virtual page number 0. This corresponds to physical page number 1111 in binary. So the actual physical address that's going to be accessed would be 1111, followed by the page offset from the virtual address, which is just copied into the physical address. So this physical address here. And also, in addition, the processor will check to make sure that the particular type of memory access that's being done, for example, is allowed. So in this particular case, we're trying to read an instruction to execute that instruction. It's an instruction fetch. But in the case of the particular access that we're doing here, because the particular entry in this table is indicating that instructions or data from this page cannot be executed, we're going to get some kind of access violation. In other words, we're trying to execute code which is stored in this page of memory, but the page table data is basically telling us we're not allowed to do this. So this would generate some kind of access violation. In other words, a hardware exception would be generated by the processor. And then lastly, I want to consider a data write to this memory location here in binary, a bunch of zeros followed by 1 followed by a bunch of zeros. So again, the processor will break this into a virtual page number part and a virtual page offset part. So the page offset is all zeros, and then the virtual page number is all zeros except for the last digit, which is a 1. So this is virtual page number 1. And then the processor will then go and look in the table up above here, seeing, is there an entry for virtual page number 1? Yes, there is. This entry here, the second one. Then it will figure out, this means that the physical page number that this address corresponds to is going to be page number 1010 in binary. So the physical address that's going to be accessed would be the physical page number 1010 plus the page offset, which is just copied from the virtual address, which is all zeros. And this particular access that we're doing is a write. So if we look at the particular entry in the table that we've hit here, this says that this particular page is writable, so the access that we're doing is allowed. So this would be allowed to proceed. And the last example I want to consider is also kind of building on the example we just went through above, which is that suppose you were asked, could the virtual address XXXX, a whole bunch of don't care bits followed by 8 zeros, could this map to this particular physical address here where the Y's denote don't care bits? And the answer is this is not possible. The reason why is that the address translation process never changes the page offset part. Whether you're talking about a virtual address or a physical address, it makes no difference. The page offset never changes. The only thing that's remapped by this address translation process is the page number. You map a virtual page number into a potentially different page number for the physical page. But the virtual page offset and the physical page offset are always the same. So the answer to this question here on the last bullet is that no, this is not possible. Now I'd like to make some additional comments about translation Lookaside buffers. They were talked about a little bit earlier, but now that we've covered a little bit more about virtual memory, I'd like to make some additional comments now. Essentially, anytime a process is running in a virtual address space, because all the addresses, all the memory accesses that are performed are with respect to virtual addresses, this means that every memory access requires an address translation. Because of this, address translation could easily become a bottleneck in the system because it's done for every memory access that's performed. So for this reason, there's typically a special cache that's used specifically for trying to speed up the translation process, which is known as a translation Lookaside buffer. Again, it's just a very specialized cache that's used to cache information about some of the most recent address translations. so that translations can be performed more quickly. So as we've seen, a cache is simply something that we provided as an input an address, and then as output it will tell us whether or not the information associated with that address is in the cache, and if it is, it gives us access to that data. If we have a system, however, that has virtual memory, this raises an interesting question with respect to caches, which is when we provide an address to the cache, should that address be a physical address or should it be a virtual address? And this leads to the following terminology. In the case of a cache that takes as an input a physical address, we refer to this as a physical cache. In the case of a cache that takes as input a virtual address, we refer to this as a virtual cache. And both of these are viable options on a system that has virtual memory. There are, however, trade-offs between these two different approaches. In other words, there's advantages and disadvantages. If we look at these diagrams that are appearing on the slide, the first of these two diagrams, the top one, shows the case of a physical cache, and the bottom diagram shows the case of a virtual cache. And the key difference between these two approaches is where the address translation takes place. So if we're running some code with the CPU and it's basically using virtual addresses for all of its memory accesses, what this means is that for every memory access that's performed, in order to use the cache, we first have to perform address translation of this virtual address into a physical address because of the fact that cache requires a physical address be provided to it. So in the top figure, we always have to perform address translation on every memory access. On the bottom diagram, we have a case of a virtual cache. And what's different here is because the cache accepts virtual addresses, no address translation is required, at least initially. We just provide the address directly from the CPU, the virtual address, to the cache. And the only time that address translation would need to be performed is if the cache misses. So we try to access the data in the cache misses, which means now we need to go out to physical memory. And when we go out to physical memory, we need to provide a physical address to physical memory. So at that point, when the cache misses, we then need to perform address translation. So that one advantage of virtual caches is that you only need to do address translation when there's a cache miss, which hopefully will be less frequent. But unfortunately, there are some downsides to virtual caches, as we'll see in a moment. At this point, I'd like to comment on some of the trade-offs between virtual and physical caches. So the main benefit of using a virtual cache is because the addresses that are involved in the case of a virtual cache are virtual addresses, no address translation is required in the case of a cache hit. It's only in the case where there's a cache miss and we need to go out to memory to populate the information in the cache that we need to perform address translation. In contrast, though, in the case of a physical cache, for every single memory access, we need to perform address translation. And because address translation has overhead associated with it, this is undesirable. With this said, however, there are a number of disadvantages of using virtual caches. Essentially, virtual caches introduce a number of complications. The first type of complication is that the same virtual address can map to distinct physical addresses. And for example, this would arise in a situation where you have a multitasking operating system where each process in the operating system runs in its own virtual address space. So because each of the address spaces of these processes are distinct, it means they have completely different sets of mappings or address translations in effect, depending on which particular process is running. So effectively, one way to combat this sort of problem is every time you do a context switch, you flush the cache, but this would not typically be very efficient. And there's other better ways to deal with this, but essentially the main point is this adds some complications to deal with. The other problem that can arise is sort of the dual to the first one, which is that two distinct virtual addresses can refer to the same physical address, and this is referred to as aliasing. You might have a situation where two different processes are sharing some memory, but the memory is actually mapped to different virtual addresses in the two different processes that are involved. And this can lead to this sort of situation. And again, there's ways to deal with this problem, but the point I want to get across is that there are additional complications that we need to deal with. And because of this, virtual caches are maybe not as attractive as they might look at first. As we've seen, virtual and physical caches each have their own advantages and disadvantages. It would be nice, however, if we could somehow combine the best of both worlds and get the advantages of virtual caches and the advantages of physical caches without getting the disadvantages of either one. And essentially, this idea leads to what's called a virtually indexed physically tagged cache, which is known by the acronym VIPT. And I think this is probably best explained, the notion of a virtually indexed physically tagged cache is probably best explained in terms of a diagram. So I'm going to defer the discussion until the next slide. I think the best way to think of a virtually indexed physically tagged cache is essentially it's a physical cache, but it's a physical cache with a particular optimization which can help to speed the cache up. And in particular, if we think about what goes on when we have to look things up in a cache, in a physical cache, there's essentially two things that consume some time. One of them is we have to perform address translation. The other thing that we need to do is once we identify which set in the cache is of interest to us, we then have to say, hey, cache, please spit out all of the entries that are in this set so that we can compare their tags and see if any of them match and we have a cache hit. So essentially, we have these two operations. There's the address translation part, and then there's a part where we say to the cache, please give us all the entries that are in a particular set, and then we have to wait for those elements to come out of the cache so that we can do a comparison of tags. And essentially what a virtually indexed physically tagged cache does is it tries to do these two operations in parallel. So the basic idea here is we make the observation that the virtual page offset, when we perform address translation, the page offset part of an address doesn't change. It's only the page numbers that get remapped. So although these bits here, which are representing the virtual page offset, are labeled as virtual page offset, we could just as easily relabel them as physical page offset because the address translation process doesn't change the page offset. And what's special about a virtually indexed physically tagged cache is the bits in the virtual address that we use to choose the particular set within the cache, which comes from the cache index. If you recall, the cache index determines the set within the cache that's of interest to us. If we choose these bits to all be taken out of the page offset part of the address, what this means is that we don't actually need to perform any address translation to figure out what the cache index is, because the page offset doesn't change. So again, although this is labeled as virtual page offset, it's also the physical page offset. So without doing any address translation, we can immediately identify which set within the cache the data is going to reside if it's in the cache. We can give this to the cache, and it can immediately start spitting out all the entries that are in that set. And then in parallel with this, the remaining bits in the address, the tag part, gets fed into the translation Lookaside buffer to do address translation. And then when finally it spits out the result of the address translation, we already have the results waiting for us to do the comparison. All of the information that's in that particular set in the cache is already waiting for the comparison. And by overlapping these two operations, we can reduce the amount of delay that's introduced by the cache. Next, I'd like to introduce some terminology that relates to cache performance. So first of all, we have what's called the hit rate, which is the fraction of memory accesses that hit in the cache. Then correspondingly, we have what's called the miss rate, which is the fraction of memory accesses that miss in the cache, which is simply 1 minus the hit rate. Then we have the miss penalty, which is how much time it takes to get something into the cache in the case that we miss. And then we have the hit time, which is the amount of time it takes to access memory when it is already in the cache, which includes, for example, the time for the tag comparison. And then the average memory access time can be computed simply by taking the hit time plus the miss rate times the miss penalty. On this slide and the next, I'd like to give some examples of the cache-related parameters for a number of real-world processors. So the first example I want to consider is the Intel Core i7 processor. So this is a 64-bit processor based on the x86 instruction set. It uses 36-bit physical addresses and 48-bit virtual addresses. It uses a 3-level cache hierarchy with a cache block size of 64 bytes. The level 1 cache is virtually indexed and physically tagged, while the level 2 and level 3 are physical caches. The translation Lookaside buffer that's employed is a 2-level translation Lookaside buffer. The page size is 4 kilobytes. And the associativity of the caches vary from anywhere from 4-way to 16-way. So the second example of a processor I'd like to consider is the ARM Cortex A8. So this particular processor is typically used in embedded applications, for example, like mobile phones. It's a 32-bit processor that's based on the ARM instruction set. Both physical and virtual addresses on this processor are 32 bits, so the size of the physical and virtual address spaces are actually the same on this processor. It employs a 2-level cache hierarchy, and the cache block size is 64 bytes. The level 1 cache is a virtually indexed and physically tagged cache, whereas the L2 cache is basically just a physical cache. The associativity varies from 4-way to 8-way, and the size of the caches vary from 16 kilobytes up to 1 megabyte. Then we have a translation Lookaside Buffer. It's fully associative with 32 entries, and the page size can vary anywhere from 4 kilobytes up to 16 megabytes. Now that we have some background on caches, we can start to, in a meaningful way, talk about cache-efficient algorithms. So the basic idea in the case of cache-efficient algorithms is to write our code in a way which maximizes locality. Because again, remember, caches are designed in order to give good performance in the case that code exhibits locality in terms of how it accesses memory. So we want to try to maximize the amount of locality in our code in order to best exploit the cache. Now, there are a number of different transformations that can be applied to code in order to increase locality. And as a matter of terminology, there's two different approaches that we can take in terms of cache-efficient algorithms. They're what are called cache-aware algorithms, and these are algorithms that have a detailed knowledge of the memory hierarchy. They know all of the cache parameters like the cache size, cache block size, the associativity of the cache, and so on for all the different levels of the caches in the system. And then the other alternative is we have what's called a Cache-Oblivious algorithm. And these algorithms have no knowledge of the particulars of the memory hierarchy. And they're designed to work in a way which just generally works well regardless of what the cache parameters happen to be. Now, there are a number of transformations that can be applied to code in order to improve the temporal and/or spatial locality properties of the code. And in what follows, we're going to look at some of these transformations. So the first transformation I want to look at is array merging. And in this situation, the particular transformation that we apply is we have data that's spread across a number of arrays, and we transform the code in such a way as by defining an aggregate type, we collect all the data together from all the arrays and instead have a single array of this aggregate type. The next transformation is what's known as loop interchange. And in this particular case, what we have is a number of nested loops, and we simply change the order of the nesting in order to achieve a better memory access pattern with respect to the cache. The next transformation is what's known as loop fusion. And in this transformation, what we do is we combine 2 or more loops together in order to get better locality. And the last transformation I want to talk about is what's known as blocking. And in this particular transformation, what we do is we group together, chunk together the data and process it in chunks in such a way as to get better locality. And I'm going to elaborate on each of these transformations that I've mentioned briefly here in terms of some code examples on the slides that follow. But before I do this, I want to introduce a short 1-slide digression just to briefly talk about row and column major order for arrays. Many algorithms employ multi-dimensional arrays, and in contexts where we care about cache efficiency, the particular layout of the data in a multi-dimensional array can become quite important. And in this regard, there's 2 very common layouts for arrays, which are referred to as row major order and column major order. So on this slide, just to simplify things, I'm showing what things look like in the case of a 2-dimensional array, but the idea extends to an arbitrary number of dimensions. On the left side of this slide, I have a figure which illustrates row major order. So in the case of row major order, rows are stored contiguously in memory. So if we walk along a single row of an array which is stored in row major order, so as I'm walking along here from left to right, I'm going through consecutive addresses in memory. The other way in which we can store things is column major order, which is illustrated in the figure on the right side of this slide. In the case of column major order, the columns are stored contiguously in memory. So as I'm walking along the elements of a column, I'm going to be proceeding through consecutive addresses in memory. And in C++, the built-in array types in the language use row major order. So earlier I talked about a number of transformations that can be applied to code in order to improve the locality properties of the code. And what I want to do now is give some code examples to actually look at some of these transformations in more detail. So the first transformation I want to look at is array merging. So here what we have is a collection of points, the x, y, and z coordinates of points in three-dimensional space. We have basically an array of x coordinates, y coordinates, and z coordinates for 32,768 points. This is probably not going to be a good way to lay out this particular data in memory for a lot of types of algorithms, because a lot of types of algorithms are probably going to process the data in these arrays on a per point basis. In other words, probably you'll get the x coordinate, y coordinate, and z coordinate for the first point, and then do some processing. And then get the x coordinate, y coordinate, and z coordinate for the second point, and then do some processing. But if we're doing an algorithm in this way, we're going to be accessing memory with a large stride. Because if we access like x subscript 0, and then y subscript 0, and then z subscript 0, we're going to be walking through memory with a large stride. We can rectify this sort of problem, though, by applying array merging. So what we do is we define some kind of type to aggregate the x, y, and z values. So I've defined this struct called point, and then we have an x, y, and z value that's stuck into this point data structure, and then we create an array of points. Now if we do some kind of processing that's on a per point basis, the x, y, and z values are all now grouped together because they're in the same struct. So if we try to do some processing with the very first point in the array, we're getting like p subscript 0. We're going to be getting the x, y, and z value, but they're all going to be consecutive in memory. And then when we go on to the next point, again, the x, y, z coordinate are all going to be contiguous in memory. So for algorithms where we want to do the processing on a per point basis, there's a big advantage to merging these arrays together. And by doing this, we can get much better locality and probably reduce the number of cache misses as a result. So the next transformation I want to consider is loop interchange. So on this slide, I have a very simple example to illustrate this particular type of transformation. What I have is an array A, which is an n by n array. And what I have in the code down below is effectively just going through, iterating over each element in the array and doubling the element by multiplying it by 2. If we look at the innermost loop, though, when we're accessing the array A, because in the innermost loop, the variable that we're changing is the variable I, this means that we're going to be walking down columns in the array. But this is very inefficient because the array is laid out in row major order. So this means we're going to be accessing memory with a very large stride, which is going to be very inefficient with respect to the cache. If, however, we simply interchange the order of these loops, instead of first looping on j and then I, we instead loop on I and then j, this can get a much more efficient code, because in this particular case, because the innermost loop now is looping over the variable j, this means that this variable here is changing, which means we're going to be walking along rows in the array. And because the array is stored in row major order, this means we're going to be walking along consecutive addresses. So we're accessing memory in a consecutive manner, which is going to be much more efficient with respect to the cache. The next transformation I'd like to consider is loop fusion. So on this slide, I have a simple example to help illustrate this particular transformation. What I have at the top of the slide is a code example where we have 4 arrays, which are n by n, called A, B, C, and D. And then I have 2 sets of nested loops. This first set of nested loops here, and then a second set of nested loops here. And each of these pairs of nested loops are doing some computation. The first one involves the arrays A, B, and C. And the second one involves the arrays D, A, and C. Now, if you look carefully at these 2 sets of nested loops, there's nothing that would prevent you from merging these 2 loop bodies together to end up with the code that's shown at the bottom of the slide here. So you've just merged the body of these 2 loops, this line here and this line here, and merged them together into the same pair of nested loops. However, the code at the bottom of the slide is going to be much more efficient with respect to the cache. Just as an example, in the code up above here, for example, at the beginning of the iteration, we're going to use the element A00 it's going to be assigned to. So we're going to set the very first element in the array A with index 0 row and 0 column and set it to some value. But then as we continue to loop, probably that value is going to be evicted from the cache because we're doing a lot of other memory accesses here. Then when we come down to this loop below and we try to use the value of A00 in this loop, most likely it's not going to be in the cache because it's been so long since we last accessed it before. Whereas if we rewrite the loop in the way that's shown at the bottom of the slide here, if, for example, if we consider the value A00 that gets written on this line here, and the very first time we're iterating through both of these loops, then we immediately use the value on the next line here. So it's very likely to be in the cache and we're going to get hit. Whereas in the code up above, this is very unlikely to happen. So the particular way we structured things, because of the type of computation that we're doing, it's much more likely that we're going to get fewer cache misses and a much more efficient use of the cache due to better locality in the bottom code. So the next type of transformation that I'd like to consider is blocking. So for this particular transformation, I'd like to consider the code on this slide, which is this naive multiply function. It takes 3 n by n matrices, A, B, and C, and essentially what it does is it computes A times B and then accumulates the result into C. Now, if you look at this particular code, it's probably written in the way that you would be most inclined to write the code if you didn't really think too much about efficiency and caching and so on. But if we look at this code, we'll notice that it's not particularly efficient with respect to the cache. And in particular, what we want to look at is this innermost loop here. In this innermost loop, the variable that's the loop variable is k. So in this innermost loop, we're going to be walking across rows of A, the A matrix, because k is varying here. And this is okay with respect to cache efficiency because the matrices are stored in row major order. So this is going to be walking across rows in A, which are consecutive in memory. The thing that's troublesome is the way that B is being accessed. Again, because k is the looping variable for the innermost loop, this variable here is going to be varying, which means that we're going to be walking down columns of the matrix B. And this is going to be very inefficient from a cache point of view because we're going to be accessing B with a very large stride due to the fact that we're walking down columns. If you look at the way that the matrix C is being accessed here, this is going to be reasonably efficient because we're essentially going to be walking through the matrix C in raster scan order, like left to right, top to bottom, and this is going to be walking through consecutive addresses. So really the problematic thing is only the way in which the matrix B is being accessed. But because of this, the cache performance of this algorithm is likely to be quite poor. In terms of a picture, the code on the previous slide has the following behavior. In the innermost loop, we're going to be scanning along a row of A, so scanning along like this. Because the matrices are stored in row major order, when we're scanning across a row, we're going to be walking through consecutive memory addresses, so this is very friendly with respect to the cache. However, when we're accessing B in the innermost loop, we're going to be scanning down a column. And because of this, we're going to be accessing memory with a large stride, and this is quite inefficient with respect to the cache. Then the matrix C is going to be accessed essentially in raster scan order. In other words, left to right, top to bottom. So we're going to be scanning across like this in the first row, and then scanning across left to right in the second row, and so on, as we proceed through the matrix C, as the algorithm goes from start to finish. So the accesses to matrix C are also quite efficient because we're essentially walking through consecutive memory addresses to access C. So the problematic thing is the matrix B. Consider what happens in the case that a single row of the matrix A and also a single column of the matrix B can't fit into the cache. So in the innermost loop, when we're scanning down this column here, the shaded column, when we read the very first element in this column, this is going to bring a bunch of surrounding elements into the cache in the same row as this element. So when we hit the top of when we start to scan the next column at the top, what would happen is that element would nominally already be in the cache, and we would get a cache hit. But if a whole column can't fit into the cache, what's happening is as we're scanning down this column, at some point, the cache entry that holds this element, and more importantly, also the element at the top of the next row or next column, is going to be evicted from the cache. So when we hit the bottom here, this element has already been evicted. And then so we're going to have a cache miss. And then when we read the next element, it also will have already been evicted, and so on, because of the fact that a full column can't fit into the cache at once. So in effect, what happens is every single read of the matrix B is going to result in a cache miss, which is very inefficient. In the case of the matrix A, things are not quite as bad. As we're scanning across this row here, because we're reading consecutive addresses in this row of A, we're going to be efficiently utilized in cache. So when we read the very first element in this row, this is going to bring a bunch of following elements in as well. So then we'll get cache hits for those next few elements, and then we'll miss, and then we'll get a few hits, and then we'll miss and get a few hits. So this will be relatively efficient. However, we have to do multiple scans over this row because we have to multiply this row times every single column in B, and there are n columns in B. So we have to scan over this row n times. And each time we start a new scan, because a single row can't fit into the cache by assumption, this means that we're going to have to reload all of that data into the cache. So we're going to get a cache miss when we start the scan over. So this is not as bad as the matrix B. We're not going to miss on every single access to A, but it's probably not as good as we could possibly do. And in the case of matrix C, things are not too bad. We're essentially going to be accessing C in raster scan order, so left to right, top to bottom, and this is basically walking through the matrix C in terms of consecutive addresses. So at least the accesses to C are relatively cache friendly. So given that this naive matrix multiply algorithm that we've been looking at so far is not very cache efficient, is there some way that we can improve upon this? And in fact, there is. We can use blocking, this particular type of transformation known as blocking. So what I've done on this slide is I've rewritten this matrix multiplication function using blocking. So it has a similar interface as before. We take 3 n by n matrices as parameters, A, B, and C. But now we have a number of additional nesting levels to our loops. And effectively what we're doing is we're processing the data in blocks or in chunks. By doing this kind of chunking or blocking of the data, we can significantly improve the locality of memory accesses in the algorithm, which was likely to result in many fewer cache misses. Unfortunately, there is a downside to this blocking transformation. If you look at the code and very quickly try to figure out what it's doing, obviously the code is quite a bit more to digest, a little more complicated to look at compared to the original code that we had previously. So unfortunately, this is one of the downsides in general to optimizing code. Often it makes the code less readable, and arguably this is the case here. To better understand what's happening in the code on the previous slide, it's probably helpful to look at things in terms of a picture. And this is what's shown on this particular slide at the top. So the basic idea with this blocking approach is we're going to process the data in the B matrix by dealing with a capital B by capital B block at a time. And we're going to fully utilize that block before we proceed on to using other data within the B matrix. So in the innermost pair of loops, which are looping over J and K in the code on the previous slide, what we're going to be doing is we're going to be multiplying a 1 by B sliver of the matrix A by a B by B block of B, and then accumulating the result in this 1 by B sliver in C. This approach will perform reasonably well with respect to caching. If we consider what memory access patterns are going to be involved in this algorithm, if we consider first of all the matrix A, essentially what happens in terms of accesses to A is we're going to repeatedly scan through the elements in this 1 by B sliver of A. So the first time we read through, because the elements are all in the same row, we're going to be reading consecutive addresses, so we'll get a lot of cache hits for that reason. Then, assuming that B is not too large, when we do the second scan through these elements here, they probably all fit into the cache and we'll get hits for every single access. So the accesses to A have pretty good locality. Then in the case of the matrix B, essentially we're only accessing elements within a B by B subblock of the matrix B at any particular time. So as long as B is not too large, probably that B by B block will fit into the cache. So we'll miss the first time that we're loading the elements in that block, but subsequently, most likely we're going to get a lot of hits in the cache. So accesses to B are reasonably good with respect to the cache. And then if we look at the matrix C, essentially when we're writing the values into this 1 by B sliver in C, we're writing the values in walking through consecutive addresses because all of these elements are in the same row, and as we proceed from left to right here, we're walking through consecutive addresses. So accesses to the matrix C are also reasonably good with respect to the cache. So by doing this sort of blocking transformation, we're able to get better cache performance than we could with the naive version of the algorithm that we started out with. So earlier I introduced the notion of cache-aware and cache-oblivious algorithms. And at this point, I just want to comment on the trade-offs between these two different approaches. So with a cache-aware approach, you require full knowledge of the memory hierarchy and cache parameters such as cache size, cache block size, the level of associativity, and so on. And this knowledge is used in order to choose key tuning parameters for the cache-aware algorithm. Now, there's some practical problems that are associated with this sort of approach. One of them is it can be difficult to obtain these cache parameters in a reliable manner. Sometimes these parameters can be determined with the help of some special CPU instructions that allow you to get information about the cache that's provided by the CPU. But even if you have such information available, such functionality available so that you can determine this information, there's another problem, which is that sometimes the effective parameters that you observe are different from the true parameters of the cache. And what I mean by this is if you have a multitasking operating system, you're performing a number of different tasks on the processor, you actually have a competition between the different processes for the cache. So although you may have a cache of a certain size, a single process is unlikely to see that full capacity available to just that process. So effectively what you see is a smaller size than the true size of the cache when you have multiple processes all competing for using the cache. And because of this, and because the workload on the system can be difficult to predict and so on, it's difficult to say what effective cache size you're going to observe. So in practice, it can be quite difficult to choose the key tuning parameters of a cache-aware algorithm in a sensible way. And if the tuning parameters are not well chosen, the performance of the cache-aware algorithm could be quite poor. In contrast, in the case of cache-oblivious algorithms, we don't require any knowledge of the memory hierarchy in caches, so we don't need to know any of those cache parameters. We don't need any magical tuning parameters that are based on knowledge about the cache. And effectively, the algorithm just auto-tunes. We can handle multi-level caches in a very automated sort of manner. And if we have a multitasking operating system, we can easily accommodate this notion of like, what's the effective size of the cache that we see as well. Because again, we're not relying on having to predict specific parameters of the underlying hardware. At this point, I'd like to introduce the notion of what's called a tall cache. And although there's a mathematical definition on this slide, I think it's probably not that helpful for understanding what a tall cache is. So I'll try to explain this from a more intuitive point of view. Basically, the idea is the following. We say that a cache is tall if the number of blocks in the cache is significantly larger than the actual block size for the cache, in such a way that as long as we have data of some size, for example, D, if D is less than the size of the cache, then the data can fit in the cache. This is essentially what it means for a cache to be tall. So if mathematically the size of the data that you want to stuff into the cache is actually smaller than the cache size, if the cache is tall, you can put it into the cache. But this is not necessarily the case that this must be guaranteed. If the cache is not tall, then it's quite possible that you might have data which is smaller than the size of the cache, but still not be able to fit into the cache. And I have a diagram here to help explain why this is so. So if we look at the diagram on this page here, what I have is an array which is stored in row major order. And then I have a small sub-block within this array, which is represented by these 4 rows A, B, C, D. So these are like subsets of 4 of the rows in my larger array. And then suppose that I have this cache down below here, which has 2 blocks in it, but the blocks are fairly large. And so like the rectangles and squares in this diagram are to scale. So the area of the area of the cache here in the diagram is bigger than the area of ABCD. So you would expect mathematically, because the area of the cache, the number of bytes in the cache is bigger than the number of bytes in the subblock, that you can fit that subblock entirely into the cache at the same time. But in fact, we can't do this. If we try to do this, what happens, for example, maybe we manage to put the part that's labeled A in the subblock into the first cache block, and then the part that's labeled B into the second cache block. But now we run out of cache blocks. We have nowhere to put C and D. So we can't actually fit this entire subblock of ABCD all into the cache at the same time. And effectively, the thing that's causing the problem here is the number of blocks in the cache is not big enough relative to the size of the blocks in the cache. So because of this, although mathematically there's enough bytes in the cache that we should be able to, in principle, hold all of the data corresponding to ABCD, because we have so small number of cache blocks, we can't actually do this. This results in a lot of wasted space. So because of this wasted space in the cache, or we're not actually storing the data we really want to, we run out before we can actually put all of our data into the cache. So this would be an example of a short cache in this particular case here. So if the cache is tall, we're guaranteed that this sort of effect can't happen. And since we're running out of time, I think I should stop here for today.